This lesson continues by having us describe the transformations that apply to the graph of y equals absolute value of x to get the graph y equals negative 1/3 times the absolute value of 2 bracket x plus 4 bracket minus 3. Then we're going to graph that new function and state the domain and range. Well, if we're given this function here, we see that a is negative 1/3, k is 2, d is negative 4, and c is negative 3. Remember, for d we changed the sign from what we see there. Well, an a value of negative 1/3 means we're going to have a reflection in the x-axis, and the 1/3, since we're multiplying that by the y-coordinate, we're going to have a vertical compression by a factor of 1/3. Our k value is 2. Well, there's no reflection, it's not negative, but we're dividing our x-coordinate by 2. So that's the same as multiplying it by a half. So we're going to have a horizontal compression by a factor of 1/2. Our d value is negative 4, so we're going to have a translation of 4 units to the left. And our c value is negative 3, so we're going to have a translation of 3 units down. Okay? Now, that's what it is verbally, but to do justice to the graphing, we should have some precise points. So what we do is we restate the equation, and we restate our a, k, d, and c values, and then we try to recall some points on the parent function. Well, y equals the absolute value of x has these 3 key points: negative 1, 1, 0, 0, and 1, 1. So we're going to take the point negative 1, 1 and put it through the mapping formula. X over k plus d, so negative 1/2 minus 4, comma, a y plus c, which is negative 1/3 times 1 minus 3. Well, when we evaluate negative 1/2 minus 4, we get negative 4.5. And when we evaluate negative 1/3 times 1 minus 3, we get negative 3 1/3. So negative 1, 1 will map onto negative 4.5, comma, negative 3 1/3. 0, 0, keeping the same a, k, d, and c values, but now using the x of 0 and the y of 0, what we get then is that 0, 0 will map onto negative 4, negative 3. And finally, we also get that the point 1, 1 will map onto 1/2 minus 4 and negative 1/3 times 1 minus 3, which is negative 3.5, comma, negative 3 1/3. So when we plot those 3 points that we just came to, those 3 points in red, here, here, and here, we get these 3 points right here. You can kind of barely see them way down there. And so now these are our 3 points, and we have an idea what the original parent function looked like. And so what we're going to try and do is graph our new function. Well, 0, 0 mapped onto this point right here. So 0, 0 acts as the corner, and so the image of 0, 0 will also act as the corner. And it also has to go through these points. So ideally we would have a straight edge, but what we can do is draw a straight line from negative 4, negative 3 through that point, and then a straight line from negative 4, negative 3 through that point. And the curve that we were asked to graph looks like this right here. Okay? It wasn't necessary for us to have that parent function graph, but it was helpful. Now, to state the domain and range, we can see that the domain is all real numbers, and the range is all real numbers less than or equal to negative 3. Okay? Alright, moving on. We're going to describe verbally the transformations that apply to the graph of y equals 1/x to obtain the graph of y equals 2 over negative, open bracket, x minus 3, close bracket, plus 1. We're then going to graph that function and state the domain and range. Okay, well, we were given this equation. On an earlier page, we said that the transformed version will be a over k, x minus d, plus c. Okay, so it'll be important for us to be able to determine those each time. That means our a value is negative 2, our k value is negative 1, our d value is 3, and our c value is 1. Well, an a value of 2 means we have a vertical stretch by a factor of 2, because we're multiplying the y-coordinate by 2. A k value of -1 means we have a reflection in the y-axis. And then a magnitude of 1 has no impact stretch-wise, so we don't have to discuss a horizontal stretch or compression because we're dividing by -1. In other words, we're dividing by a magnitude of 1. Now our d value is 3, so we're going to translate 3 units to the right, and our c value is 1, we're going to translate 1 unit up. These are the verbal the description of the transformations. But what would it be if we tried to plot points with great accuracy? Well, we remember our mapping formula, all right, our really important page from our first half of our lesson, and that's our mapping formula. Now we know 2 points on our parent function that are key, are -1, -1, and 1, 1. And also we need to remember that our parent function has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So these 4 pieces of information are key. Well, what we're going to do first is figure out the image of the point -1, -1. Well, xy maps onto x over k plus d, ay plus c. Evaluating that, we get 1 plus 3, comma, -2 plus 1, which is 4, -1. The other point we have is 1, 1. Well, that maps onto 1 over -1 plus 3, comma, 2 times 1 plus 1. And when we evaluate that, we get -1 plus 3, comma, 2 plus 1. This evaluates to 2, and this evaluates to 3. And we get the point 2, 3. So these are the 2 important points that we have. Now let's see if we can do any work with these asymptotes. What we get with those asymptotes, first of all, we realize that we have an asymptote at y equals 0. There's no x here, and so what we're going to do is see what does the y transform to in our mapping formula. Now remember, xy maps onto x over k plus d and ay plus c. Well, that means that the y is mapping onto ay plus c. Okay? So y maps onto ay plus c. Well, if y is 0, that's going to map onto 2 times 0 plus 1, which is the same as 0 plus 1, which is 1. That means we have a horizontal asymptote for our function at y equals 1. Similarly, when we look at our mapping formula, we see that x maps onto x over k plus d. Well, that means that we're going to have here x maps onto x over k plus d. Since we're talking about an x value of 0, that's going to map onto 0 over -1 plus 3, and that's going to equal 3. So we see we have a vertical asymptote at x equals 3. And so now we've evaluated that. Now, to give you a little quick tip, in the case of the parent function y equals 1 over x, after you transform it, you'll always have a horizontal asymptote at y equals c, and you'll always have a vertical asymptote at x equals d. And if you're not sure what I mean by that, let's look at the original question. Originally we said that the d value was 3 and the c value was 1. Well, our vertical asymptote will always be x equals d, so in this case x equals 3. And our horizontal asymptote will always be y equals c, which in this case is y equals 1. Okay? So now we know some good information about this curve, and we can do some graphing. Now, this is a little bit complicated to look at first. I want you to remember that the y-axis and the x-axis are sacred. They don't move. Okay? They stay still. However, it's effective for us to know what our vertical and horizontal asymptotes are. There's our horizontal asymptote, y equals 1, and there's our vertical asymptote, x equals 3. So even though the origin is still here, it's good for us to sort of see these two lines providing a guide to the behavior of this particular curve. Well, we also know that one of our points transformed to here, and another one of our points transformed to here. And we're going to try and draw a graph that behaves the same way as the black graph, but does so respecting these asymptote lines. So what we're going to do is draw, with a little bit of practice, it becomes kind of second nature. we're going to draw that curve for this quadrant. See, we've got this point, but we still have to treat the asymptotes like asymptotes. And similarly for this one, we're going to draw our curve. We're going to make sure it goes through that point, but we're still going to treat our asymptotes like asymptotes. So the x and y axis are still here, and our pink curve looks like this. The red asymptote lines aren't really there. They're just providing us a guide for our sketch. Okay? And so you might say, well, what are the domain and range of this pink two-part curve? Well, we see that the only x value that the pink curve cannot ever get to is an x value of 3, and the only value of y that the pink curve can't ever get to is a y value of 1. And so the x and y axis are no longer asymptotes for the pink curve. Only these red asymptote lines are. So what we get is a domain of x can't equal 3 and a range of y can't equal 1. Okay? And for our final one, we're going to verbally describe the transformations that apply to the graph of y equals x cubed to get the graph of this function. And then we're going to state the domain and range. Well, if we're given y equals -2 times 1/3 of x times x plus 1 quantity cubed plus 4, we see that a is -2, k is 1/3, d is -1, and c is 4. Well, when a is -2, we begin with a reflection in the x-axis. Since we're multiplying the y-coordinates then by a magnitude of 2, we say we have a vertical stretch by a factor of 2. When we say k is 1/3, we know we're dividing our x-coordinate by that. So dividing by 1/3 is like multiplying by 3. We can say we have a horizontal stretch by a factor of 3. When d equals -1, that means we translate 1 unit left, and when c equals 4, we translate 4 units up. Now algebraically you might wonder what this looks like. Well, given this is our original function, we have a equals -2, k is 1/3, d is -1, and c is 4. We have our original graphing formula. And now we're going to go back to points that appeared on our parent function. -1, -1, 0, 0, and 1, 1. Well, we know that -1, -1 will map onto -1 over k plus d, a times -1 plus c. And when we do a little bit of math, on the left-hand side of the comma we get -4, and on the right-hand side we get 6. 0, 0 will map onto 0 minus 1 comma 0 plus 4, which is -1, 4. And finally 1, 1 will map onto 1 over 1/3 minus 1 comma -2 times 1 plus 4, which is the same as 3 minus 1 comma -2 plus 4, which is the same as 2, 2. So now what we can do is graph these 3 points, -4, 6, -1, 4, and 2, 2. And so we do so, and we see them right here. Okay? Now, since we're drawing a transformation of a cubic function, it's good to remember what the original parent function of y equals x cubed looks like. The origin is here, and the image of the origin is now here. And so what I need to do is somehow draw a curve that looks like this through that point, and that behaves the same way. Well, what we get is a curve that looks something like that. Okay? So we treat the origin the same way as best we can that the origin was treated here, while still going through the required points. And you might say, well, what's our domain here? Well, it's x element of the reals. And what's our range? Well, any y such that the y is the element of the reals. And so our domain is the set of real numbers, and our range is the set of real numbers.